All right, today we're going to focus on complex numbers and finding complex solutions for polynomials. In order to get that started, we're going to talk a little bit about polynomials. It tells us here that a variable in the complex number system is referred to as a complex variable. And a complex polynomial function, f of degree n, is a function in this form right here where we start with the highest exponent and then go down in order. It's going to tell us here that some of the solutions can be complex and some of them can be real solutions. We're going to focus on the complex ones, and by that we mean that the polynomial has an imaginary solution. If f of x is a polynomial degree n, it has exactly n zeros in the complex number system, including both real and complex or imaginary. So in Algebra 2, you heard these called imaginary. The complex number system is both the real and the imaginary ones. And so we had already talked that a polynomial of the degree n has n zeros. So something like this with a 2 here, that's a second degree polynomial, will have at most 2 zeros or solutions. They can both be imaginary or they can be real, either one. So we're going to do both of them here, and we practice a couple different ways of solving polynomials. We've factored, we've used the quadratic formula, we use synthetic and long division to help us get down to those zeros. So that's what we're going to do today, is kind of put it together. So on our first one here, if we want to solve this quadratic, first thing I would do is set it equal to 0. Now this is one that factors, so I can go ahead and factor this. That's going to be the easiest way to solve a polynomial. In this case, both of those come out to be the same thing, x minus 3 times x minus 3. And so our solution would be 3, because 3 minus 3 makes that 0. It is considered a double solution because both of them are the same, so it's got that multiplicity of 2. Remember, it'd be tangent at that point because of the 2 degree. All right, on this one here, they gave it factored for us. When it is factored, again, I would set it equal to 0. And they've made it a little bit easier than this one, because this one I had to factor to get the solutions, but since this is factored, I can go ahead and get our solutions. Now, the one that students miss most often is this one right here, this x to the 4th. If that was 0, then the whole thing would be 0. So 0 is one of my solutions. We don't usually write that as x minus 0 to the 4th power, but you can think of it that way when you think about your factored form, x minus a root. The next one would be 5, because 5 minus 5 makes that 0, and our last one here would be 1 minus 1. And so this right here has a multiplicity of 4, so remember that's going to be tangent there. This one has a multiplicity of 3, so it's going to be a point of inflection, and this one has a multiplicity of 2, so it's going to be tangent at that point as well. So this has a multiplicity of 4, this has a multiplicity of 3, and this has a multiplicity of 2, so that is considered the 9 solutions for that polynomial. If you multiplied it out, that would be the degree. All right, our next one here, again, I have to factor first. And so I would set it equal to 0, and I'm going to factor out an x there because there's a GCF on those. And so I'm left with x squared plus 4. Now, we just talked about this one. That's one that students miss often, but you don't want to miss it. So that's x equals 0. That would be my first solution. With this one, I set this equal to 0, and I'm going to solve here. And so I subtract the 4 to get it to the other side, and I get x squared equals negative 4. Now, when we take the square root here, we end up with a negative under the square root. That's where those imaginary solutions come from. The square root here cancels out. Anytime we take a square root of a square, you need the plus or minus. So that's going to be my plus or minus there. And when we have a negative under the square root, we said that's going to give us our I. And so the square root of 4 is 2, and that square root of negative 1 is I, so that would be x equals plus or minus 2i. When we have a complex solution, you've got to have both the negative and the positive. You never just have one of them. So this is one solution would be positive 2i, the other one would be negative 2i. They come in pairs. And so here we have 3 solutions, which was the degree of this one. So we found the max number of solutions for that one. It's got 1 real solution, 2 imaginary ones. All right, for our next one here, this is another one that factors, so we can go ahead and factor that when we set it equal to 0. It's a little bit trickier to factor this one. That's an x to the fourth, so that would be x squared times x squared. And then we're looking for what multiplies to be 4 and adds to be 5. And so that is a positive 4 and a positive 1. Now, these I have to set equal to 0 because that's an x squared, not an x. And so x squared plus 4 equals 0 and x squared plus 1 equals 0. Now I'm going to solve each one to get my x value. And so I get x squared equals negative 4. I take the square root of both sides. Remember that plus or minus. Anytime you take the square root of a square, you need that plus or minus. 2i. So there we have two imaginary solutions. I subtract this 1 to get it to the other side. Take the square root, and I get x equals plus or minus I. So all 4 of the solutions on this particular polynomial are complex solutions. So it's not going to actually touch the x-axis. That's when you get those imaginary solutions, when it doesn't touch the x-axis. And so we have 4 solutions. Remember, this is the max number of solutions is your degree of the polynomial, and we have all 4 of them right here. 2 of them positive 2i and negative 2i, and positive I and negative I. So that's got 4 imaginary solutions. All right, for our next one, this is one of those pattern factoring that you have to remember, because that's the difference of 2 cubes. And so it's my first one minus my second one, and what's being cubed to get 8 would be 2. Then I square the first one, plus multiply the 2 together, and then square my last one. So that's the factored form. This first one, that's x equals 2. That's my solution there because it's always x minus my root, or 2 minus 2 makes that 0, however you want to think about that. Now this one does not factor. So I'm not sure what I'm doing here. Sorry about that. This one does not factor, so I am going to have to use the quadratic formula. You're going to have to dig deep back in Algebra 1 when you learn that quadratic formula. That helps us when you can't factor. Factoring is the easiest way to solve, but if you can't factor, that's a possible way. So that's negative b, and b is my middle term right here, plus or minus the square root, b squared, so that's going to be 4. There's my b, I'm going to square that, minus 4 times my a value, which is what's in front of the x squared, that's 1, times my c value, which is 4, all over to a, which is 1. So I'm just going to leave that as 2. Now with this here, take your time simplifying that, because we find students make a lot of careless mistakes when they're trying to do the simplification all in one time. So I'm going to leave that negative 2 plus or minus, and in here I get 4 minus a negative 4 times 4 is 16. All over 2. And so we get negative 2 plus or minus, that's going to be the square root of negative 12 over 2. Now we're going to simplify that radical as we take it out, and we need an I because we've got the negative under the square root. Anytime you get that negative under the square root, you're going to end up with an I. And so 4 is the biggest perfect square that goes into 12, and so I would get 2i, and 4 times 3 gives me 12. Now that's a perfectly good answer right there. You can stop there, or you can go ahead and reduce, whichever way you want to do that. 2 goes into all of these, so I can reduce this by 2. And so that's going to give me a negative 1 plus or minus I root 3. Sorry about that. I ran out of space there, so it's not too much of space, but that would be our solution. So those are the ones we're focusing on today, are the ones that are imaginary solutions. An equation can have both real and imaginary. It can have all imaginary like we see here, and again, a real and imaginary, and you do have to use all your tools to solve for those solutions. All right, the next thing we're going to look at is this theorem here. It says every complex polynomial function with a degree of higher than 1 can be factored into linear factors, not necessarily distinct of the form. So here is our polynomial in the factored form. You saw this in quadratics in Algebra 1. We always write it as x minus my first root, x minus my second root. Well, with polynomials, you can have a number of those depending on the degree. So if it's a degree 2, like a quadratic, you would only have 2. If it was a cubic, you would have 3, and so on. It says, let f of x be a polynomial function whose coefficients are real numbers. If r is equal to a plus bi is a 0 of f, the complex conjugate a minus bi is also a 0. Okay, so I kind of said that earlier, and not those technical terms. Sorry about that, guys. All right, so a polynomial function of function f of degree 5, whose coefficients are real numbers, has the zeros 1, 5i, and 1 plus I. Find the remaining zeros. Okay, so we said if there's an a plus bi, there is an a minus bi. And I told you that up here. When there's a positive one, there's a negative one. Those always come in pairs. Your imaginary solutions always come in pairs. That means if we're looking for a polynomial that has these solutions, if it's got 5i, then you need to know that it also has negative 5i. And if it's got 1 plus I, then it also has 1 minus I. Those come in pairs, so they has to have both of those. That's what we found up here. Notice that when we get an I, it's when we're simplifying our quadratic formula here, so it's got the plus or minus there, the positive one and the negative one, that's 2. And when we were simplifying here, it's got the plus or minus, so again, you got a positive and a negative one. Now, if we were to write this in that factored form like we read right here, that's going to be x minus my first root, which is 1, x minus my second root, which is 5i, x minus my third root, which is a negative 5i, so that turns into plus. And then you would write x minus, the root is 1 plus I, and so you need all of that there. And then x minus my final one, which is 1 minus I. And I know that looks really complicated, but if you actually multiplied it out, the i's would get canceled out and you would only have real numbers. Because these I values do come from real numbers. This entire polynomial was real number, but once we solved it, it had those imaginary ones. That means that when we multiply this out, all of those i's would go away and we would just have real numbers again for our polynomial. Let's look at that back here. All right, it says a polynomial function of f of degree 4, whose coefficients are real numbers, has the zeros 1, 1, and negative 4 plus I. Find the remaining zeros, then write the equation of the polynomial in standard form. And we're not going to go all the way in standard form because that's going to be tedious, but I will show you some of it so you can see where it's coming from. So x minus 1 squared, because both of those are a 0, 1. So x minus my root, and there's 2 of them. Then I would get x minus negative 4 plus I. And we said if there's a negative 4 plus I, there has to be a negative 4 minus I as well. The one I'm going to show you how to multiply is this, because that's the one that you really haven't worked with. So let's do that. I know you guys can foil that on your own. So we're going to work with this one. The first thing I'm going to do is distribute that negative right there into this so it makes it a little bit easier to look at. So a negative times the negative, it gives me a 4. And then a negative times the I gives me a negative I. I'm going to do the same thing for this one. And so I get plus 4 plus I. Oops, I don't need 2 parentheses anymore. All right, so now we've got these two right here. I'm going to keep multiplying that out so you can see that it does become real numbers. And so this is where we would want to multiply this out. We're going to distribute that x to everything in there, the 4 to everything in the other one, and then the negative I to everything in the other one. So x times x gives me x squared, 4x, and 4i. I just distributed that x to everything in there. Now I'm going to distribute the 4 to everything in there. And so that gives me 4x plus 16 plus 4i. Now I'm going to distribute this negative I. And so I get negative xi, negative 4i, and negative I squared. All right, I wrote this incorrect here. That should be an xi. Sorry about that if you'll change that. X times I gives us xi. I wrote 4i there. It should be an xi. All right, so now we're ready to simplify this. We have a xi and a negative xi, so that's going to cancel. We have a 4i and a negative 4i, that's going to cancel. On the most part, those i's are always going to cancel. That's why there's the two signs for them. You're always going to end up with a positive and a negative. Because this comes from real numbers, you're not going to end up with those i's at the end. Now, you're probably thinking, well, that one hasn't canceled. But remember the definition of I was the square root of -1. And so if we squared both sides there, then we would get that I squared is -1. And so if I squared is -1, then this right here is a negative times a positive, which turns that into +1. So that I also goes away. So we've got a 4x and a 4x, which give us 8x. And then we've got a 16 and a 1, which gives us 17. Notice there's no i's there now. It's a regular polynomial. In order to get it to the standard form, we would have to FOIL this one out and then multiply that times this. That's kind of tedious, so I'm not going to go through all of that algebra 2. But I did want to show you that you can go, that if you have an I, when you start multiplying it out, you're going to end up with a polynomial with only real numbers. All right, here's this last thing I'm going to show you here. Or, sorry, two more things. Use the given 0 of the polynomial to find all the remaining zeros. All right, so if we have a -5i, we know there also has to be a positive 5i. So these two zeros are coming from this right here. So the first thing I'm going to do is I'm going to write two factors, x minus 5i, x plus 5i. There's my two factors, x minus my first root, x minus my second root. That's going to give me this right here. Well, we just learned if we FOIL this, we're going to get rid of those i's. So x times x is x squared. X times 5i gives me 5xi. Negative 5i times x gives me a negative xi, negative 5xi. And then a negative 5i times a 5i gives us a negative 25i squared. Again, these cancel. And so we just need this one right here. We said I squared is -1, so that turns that into a plus 25. And so I know this right here is one of the factors that goes into this equation. Well, to find the last one, all I have to do is long division. Remember, we went through long division and we said we can take something that's cubed here and take it down if we divide by one of the factors. So I'm going to do my x squared plus 25. And we're going to do our long division. With long division, I take my first term and divide by my first term. So x cubed divided by x squared is x. I like to keep everything lined up. It makes it easier. X times x gives me x cubed. X times 25 gives me 25x. Now we subtract that second row. And so x cubed minus x cubed is 0. 3x squared minus nothing is just 3x squared. 25x minus 25x is 0. And so our 75 comes down. I do it again, and 3x squared divided by x squared is 3. I multiply that, and I get 3x squared and 75, and I'm going to multiply that, and we get a remainder of 0. We knew we were going to get a remainder of 0 because we knew this was a factor since they gave us the zeros, and in order for it to be a factor, the remainder has to be 0. We talked about that earlier when we did long division synthetic. But now I can write this in the factored form because there are my two factors, x plus 3 and x squared plus 25. And so this one, this 0 would be -3. And then we already know the zeros for that one are plus or minus 5i. So there's our 3 zeros for our cubic. Remember, this is always the max number of zeros is that degree of the function. All right, the last question. Find the zeros of the polynomial function. Here. In this case, they gave it to us the hardest way they can give it. So in this case, that would be the hardest way that we would do it. You would have to use your P and Q that we learned last time to get the maximum number of solutions, and then you would have to start testing those. And as you place them in, you would find a real one and then use it to find the imaginary ones. We're not going to go that far here in on-level pre-cal, so I'm not going to confuse you with that one. I want you to focus on what you could do. or what we need you to do here. So one of them is if you have a negative or a positive imaginary root, know that the other one exists. You should be able to multiply them out to get rid of the i's. And you should be able to solve for them like we did in both of these cases, either through factoring or the quadratic formula. That's what you really need to be able to get out of this lesson, that you can solve for an imaginary number, and that you can work backwards to multiply that imaginary number to get rid of the i's. All right, thanks.